So today we are talking about, where'd my pen go? Exponential growth. Exponential growth. So you will want to take a few notes today. So I think most of you already have your notebook out, but there are a few things you're going to want to write down. Now we've been talking about exponentials, right? So you know that that's going to still be involved. But if we're talking about exponential growth, what do you think that means? With growing, right? Probably something that looks more like this, where we're growing and increasing instead of something that looks like this, where we're decreasing, negatively growing. That's one way to think about it. But exponential growth, maybe we haven't heard it before, it sounds really mathy, but we kind of have a pretty good idea of what this is. So our learning target, students will be able to write and evaluate exponential growth functions. So we can write exponential growth and we can evaluate. So we can use a function to solve a problem. So this isn't something you necessarily have to write down. This is our technical definition of exponential growth. So exponential growth occurs when a quantity increases by the same factor over equal intervals of time. So all that is saying is exponential growth happens when we're increasing by the same amount. That's all that means. Again, we don't need to get that whole definition down because we're going to look at really the formula for exponential growth, a couple of different aspects of exponential growth. So we're just talking about something that is consistently increasing. The other thing to pay attention to here is exponential growth. It talks about, there we go. It talks about over intervals of time. Now all of these things we're going to talk about eventually compound interest, where things are happening over a certain amount of months or years or half a year or something like that. So time is going to play a big role with this exponential growth. Now here is the exponential growth function. So this is something you're going to want to write down. Here's our function for growth. Now the first thing that we need to notice is that this is still an exponential function, meaning it is still in this form of y equals a times b to the x. Right? We still have our a value out in front, but instead of just writing b, we've replaced b with 1 plus, and we'll talk about this r. But it's still in that exponential form. We're just adjusting a little bit what that b value looks like. This is 1 equal there. Or about the same as what it is here. Definitely not there. So, our y value is our final amount. No surprise there. I don't really love that wording of final amount, but that's kind of our total. Our a value, instead of calling it our y-intercept, that's still true, it is our y-intercept if we look at a table, but it's our initial amount or our starting amount. And then our stuff inside the parentheses, we always start with 1. We're going to be working with a lot of percents and things like that. And that r value is our rate of growth. So we'll do 1 plus our rate of growth, and then our exponent, instead of being to the x, represents time. So make sure, really, if we're looking at this slide, we want to have that equation down here. We'll have that in each of those labels for each part. So when we're dealing with exponential growth, here's an example of a question that we would see. The function y equals 150,000 times 1.1 to the t. So notice that already is in our regular exponential form that we've seen. Y equals a times b to the x, except it's b to the t because we're dealing with time. So the function represents the attendance y, so y equals our total attendance, at a music festival T years after 2010. All right, so leading up to 2010, they took like tickets or whatever, and they found, all right, we are growing by about this much per year. And here's the equation they came up with from that. So by what percent does the festival attendance increase each year? Well, if we look, remember, inside those parentheses, we call that our growth factor. And we know that it has to start out with 1 plus r, right? That's what it has in here, 1 plus r. That this equals 1.1. So if we're looking for our growth, or our increase in attendance, we're really looking for our rate of growth. We're looking for this R value, is what they want. Remember, R starts with 1, so that R value is just going to be 0.1, where we would say it increased by 10% every year. 1 times 1? Oh, that's supposed to be 1.1. That's 1. So over here, good question. Over here in our equation, this was our growth factor, right here in those parentheses. And what they were looking for, I know is strangely worded in this question, in letter A, but what they were looking for is they really should have said, what is R equal? What is our rate of growth each year? So we subtracted 1 from each side because we were looking for this R value. We're looking for the rate of growth. We always start out with 1. We can't be less than 1, because if we were less than 1, we would be decaying. So we have to start out with 1. And then that R is what we're growing. By what percent or what decimal are we growing? So if I gave you something and our rate of growth was 1.25, then we could quickly see our growth factor, sorry, you get my vocab now better. Our growth factor is 1.25, and we could see that our rate of growth was just 0.25, right? So whatever's left over after we subtract 1. We'll look at more problems like that. I know it sounds like it's a foreign idea right now. We'll look at a lot more problems like that. How many people attended the festival in 2014? Round your answers to the nearest 10,000. So, what we look to do there is we take our equation. And remember, T represents time. So between 2010, where we started, and 2014, there were 4 years. We replace T with 4. And we would get, I can't do that in my head, I have it written down. It's 200,000. We get 219,615. So again, they collected this data and they said, all right, our festival is growing by 10% every single year. And they said at year 0, or in 2010, at year 0, we had 150,000 people. So if we're growing at 10% each year, which is all that this says here in our parentheses, then we can project, all right, what do we think, how many people do we think we're going to have in 4 years? So it's just a guess that if we keep growing at 10% every year, we'll have 219,615 people 4 years down the road. So now it's your turn. Take just a couple minutes. We're going through those same steps that we just talked about, except this time we have a different function. The number of members of a website after T years after 2010. So first, by what percent does the website membership increase? The Let's going back to this first question here. How many members will there be in 2016? So 6 years down the road, how many members will there be? Take about 2 minutes. Give those a try. I'll need to see, to get your homework paper today, I'll need to see these done and one more at the end. So it is important that you try this. Second one. I know your first one looks good. That's not what I got for part B, so I can look again. Oh, you did? Oh, on mine I didn't round. Does it say round? It's near 100,000. Let me see. That's what I got. I didn't round mine. So for part A, remember all we're looking for is that rate of growth. Which, if we set up an equation, it would look like this. We really don't have to set up an equation. We just know that we're subtracting 1 from whatever is in our parentheses. So our rate of growth, 0.15. And if they say rate it as a percent, we're moving that decimal over twice. So it'd be 15% is the rate of growth. Every year, they're increasing by 15% in their members. In part B, all we're doing is saying, hey, 6 years down the road, about how many members will we have if we continue with the same rate of growth? And it says round your answer. So if you did not round, it would be 1,156,530 members. Round your answer to the nearest 100,000. So about 1.2 million if you rounded. About 1.2 million. Now, we're switching gears a little bit. Compound interest. Where have you heard, or have you heard the word compound interest? If so, do you know where, or where that term is used a lot of times? In math? Outside of math? Not sure? Skylar? Yeah, banking. Nice. Good job. Well, it's good you remember that. In a bank, a lot of times they talk about different interest rates, or if you have money in the bank, they're talking about how are you getting interest on that money in the bank. Because you do understand that when you put money in the bank, it's not like it just sits there, right? The bank uses it for like for loans and things like that. So technically, banks pay you a little bit. They give you interest on the money that you hold in the bank. So they kind of, in a sense, pay you to keep your money in their bank because they use your money for other things. So a lot of times, anyway, with banks, they talk about compound interest and how quickly interest on your money in the bank, or your principal, is what they call it a lot of times too, how quickly that incurs interest. So interest could happen. You could get interest on your money in the bank every year. They might say, hey, we'll give you 4.5% interest on whatever money you have in the bank. That means of whatever money you keep in their bank every year, they'll give you 4.5% back, kind of as you could call it a payment for keeping your money in their bank. You might also hear that they'll give you maybe 2% semi-annually. Now, how often is semi-annually? What is semi-annual? How often is that? Semi what? Often. More specific. Every month, every 2 months, not the same time. When we hear semi-annually, that would mean every 6 months. What about quarterly? Every 3 months. You don't have to write this down, I just want to get us on the same page. What about monthly? Yes, by month. Very good. Yeah. So we'll say 1 month. So we'll hear things like annually, semi-annually, quarterly, monthly is a little more straightforward, but we'll hear these terms when we're talking about compound interest. So now we have another formula that deals with compound interest. Now it looks complicated and maybe not scary, but it keeps the same, notice it keeps the same elements that our exponential formula has, right? We still have an a value out in front, except this time we call it the principal. We still have a b value inside the parentheses, and we're still going to an exponent. Our variable is still going to be an exponent. So take a second, write that down, write what each of those mean down, and I'll talk about it for a second. Random, not really random, but side note question as you're writing those down. Would you guys rather be in rows, or do you like being in pods? Or does it not matter? You like being in pods? I just don't know if it's really annoying to have to sit like Tab is, like sit completely facing the board, or to have to turn all the time. Turn your head. You might walk in tomorrow and be in rows. We'll see. In the same general area. We'll figure that out with time. So, P, the starting value, is our principal. So, if you open a bank account today, and let's say you put $1,000 in the bank account to start out, when you open it, that $1,000 would be your principal, your initial amount, your starting amount. R, right up here, is the annual interest rate. So notice it says annual, so yearly interest rate. So if they give us an interest rate and say that, hey, every quarter it's 2.5%, then we're going to have to, and I won't get into it right now, but we're going to have to do some work to get it to be annual, because we want that number to be yearly. T is time. Still, almost always when we see T in the equation in math, it's time. So hopefully that's something we get a little bit used to. And then lastly, this N, the number of times interest is compounded per year. So if they say you have 2.5% interest, it's compounded semi-annually, that means that it's compounded 2 times per year. So we need to plug that in for N. Let's take a look at an example. You deposit $100 in a savings account that earns 5% annual interest. So every year, you're getting $5, compounded yearly. Write a function for the balance after T years. So we know it has to be in the form that we talked about right up here. Now our principal, again, is our starting amount. So you start out by putting $100 in. Now 1 plus. And R, our annual interest rate. We have to put it in decimal form. So account that earns 5% annual interest. So in decimal form, 0.05. And then remember, our N is number of times interest is compounded per year. This tells us we are compounded yearly. So it's just 1 time per year. And then we need to fill in. We need to fill in up here our N, number of times per year, times T over time. So it would be 1 times T. So if we were to write this cleanly, 100, 1 plus 0, T, we need to take one more step, 100, so a good strategy with these is when you're looking at these problems, write what our general formula is, and then just fill in what we know and simplify from there. Because we have worked with, for a couple of days now, this at the bottom. So we're getting more comfortable with something in exponential form. But this top one looks really complicated. We don't like to work with something that's overly complicated. Now it's your turn. The table shows the balance of a money market account over time. So this table shows what's happening over time. They start out by putting $100 in the account. After year 1, they have 110. Year 2, 121. Year 3, and so on. So they want us to write a function, compound interest that looks like this. That represents the balance after T years. All it means is we need to write an equation so that I can ask you, hey, what's the balance going to be in 22 years? And you're going to be able to plug 22 in and find out. So if we start out, y equals, what would our principal be? What would our starting amount be? Say again. 100. Yep. Because at year 0, at time 0, we put $100 in. Now, if we're keeping the fill in our equation, it would be 1 plus. Now, this is where things get a little bit tricky. We need to be able to find out what is going on year after year. So grab your calculator again and type in 100 divided by 110. Whoops, just kidding. There we go. Type in 110 divided by 100. My fault, other way. 110 divided by 100. What do we get? So we have a 1.1 from there to there. Okay, do 121 divided by 110. What do we get? 1.1. So what that's showing us is that our growth rate is 1.1. Let's see, am I getting my terminology exactly how I want it? Yeah, our growth rate is 1.1. Or a growth factor is 1.1. There we go. So that means our interest rate, if our growth factor is 1.1, then what is our interest rate? What did we talk about earlier? It's just 0.1. Yep. So 1 plus 0.1. What are we missing still? Number of times per year. Well, this is just once every year times once per year times our time. So if we are writing, and I'll need to see this written down on your paper as well before you get your worksheet. You have 100 times 1.1 to the t. Now, if we want to figure out how much money will be in the account after 8 years, how do we find that? Put it all to the 8th. We put 8 in for t, because t, remember, is our time. So, last thing before you get your worksheet. This is the practice problem you'll do. What? Didn't we just do that one? Oh, shoot. We did the bottom one. You'll have to do, this top one is different. That's what it was. So if you didn't finish the bottom one, there it is again. This top one is what we did with that compound interest. But just as a quick review before you do that, we talked about really two things today. We talked about this general idea of exponential growth, that when we have an exponential equation, that we consider exponential growth if our b value, remember this is just our b value, is greater than 1. That's exponential growth, because our graph will slowly, well, maybe not slowly, but will be growing. So it's a general idea of exponential growth. We looked at one specific and very common example of exponential growth, or aspect of exponential growth, and that is this idea of compound interest. And the formula that we use to find compound interest is right here. And we're using a lot of the same factors, but we just give it different names, like principal, interest rate, and things like that. The reason we like, last thing I'll let you do your practice, the reason we like compound interest is because if you start out at year 0 and you put $100 in the bank, and let's say they give you 5% annually, okay, in year 1, you'll have $105 just from that same 100 in the beginning. Now, in year 2, you don't want them to take 5% of 100, right? Because now you have $105 in the bank. So what compound interest does is takes 5% of that 105. It'd be like 112 or 111, something like that. Oh, not even. 110 point something. Now in year 3, you don't want them to take 5% of this $100. You want them to take 5% of your money from last year. So they take 5% from that. So you could see, I mean, with $100, it's not a huge difference, but you could see over time and with larger amounts of money why you would want them to take last year's, or the compounded year's, interest, not just stick with this first year's. Does that kind of make sense? It gives you more money. So we like compounding.